Okay.
It should be fine.
Now it's fine, right? So we don't need a dedicated microphone.
I can hear it. It's okay because I can hear you.
Okay.
Yeah, everything is okay.
Come on, Hans. Right, so welcome everyone in person and online. It's my great pleasure today to introduce our speaker of the day. It's Hans Huebl. Hans from Germany at the Walter Marsan Institute for the Bavarian Academy of Sciences in Munich. So Hans did his PhD in 2007 at the Technical University of Munich. After that, he had a rather short stint, 1.5 years of postdoc with Andy Morello in Australia and the University of New South Wales. And after that, he came directly to Walter Marsan Institute in Munich to start working on his habilitation. And after he earned his habilitation and after doing excellent work over the years, he was promoted to be the deputy director of this rather big center. And now he's serving as the deputy director there. And he is one of the main PIs of Munich Center for Quantum Science and Technology, which is a large consortium funded by the German and Bavarian government. So I'm very happy that Hans is here to tell us about his work, but I also on a little bit personal note, I'm extra happy today because Hans was one of my 3 PhD advisors. So I owe a lot of what I have learned to his guidance, and I'm really happy to be his host today. So Hans, please, we are looking forward to your talk.
Thank you, Akash, for this kind introduction. You can actually tell, so as I'm an experimental physicist, how well I did my job as a co-supervisor of Akash's thesis, because he left the experimental realm and kind of chose to do theory only, which is a supervised decision, Akash, and you're doing excellent work, and it's happy to collaborate with you. But on the other hand, on a positive note, it's also nice because you can understand us experimentalists and understand our whinging about experimental pitfalls and difficulties. So thank you for inviting me. Thank you for having me. I'm presenting a part of my science interest, which is maybe less familiar to Akash, and that's on purpose. And I want to encourage you to kind of ask questions in between if something is unclear. I learned that you are a solid state community, and I'm a solid state scientist, solid state physicist. But if I'm kind of deviating too much or kind of assume too much of you, just stop me and I try to fill in the gaps. So I want to talk about sensing. Akash already told you where the funding is coming from. The funding is coming from the German Science Foundation in terms of this cluster of excellence. And there's also money coming from the European Union in terms of this MAC-SENS consortium, which is our main funding for doing mechanics or nanoelectromechanics, which I will also talk about. And I want to actually start my talk with
the pointers will be working.
I run out of battery, so but that's not a problem. No issue, okay. So I want to start with thanking the people who actually did the work and who actually work on all the details which make this work possible. And there are a lot of intricate details and experimental challenges which have been solved by mainly the students. And I'm just here the humble presenter who's presenting their work. It is really a pleasure working with the students and kind of sort out all these challenges to get things done. And I also want to acknowledge theory collaborations for the presenter for the work I present today with Stefan Rotter's group from the TU of Vienna. He helped us a lot with spins, and Alva Sanchez from Barcelona, who helped us a lot in understanding mechanics and streets and how they work together in this work. So When I think about quantum science, and you see the kind of side note that's from a superconducting circuits perspective, I have basically the following topics in mind. So quantum information, computing, communication, sensing, and matter. So typically what I see is the kind of a set of challenges connected to those topics. State generation, it depends on which of the topics you are in, if this is kind of more or less established. Then always the question is, how long is this quantum state lived? Can we convert these states between different excitation forms? Meaning that you would like to think about quantum communications where you would love to transfer from a quantum microwave state to an optical state for long-range communications, for example, or even in a sensing context where you say, okay, I have a sensor that might be a spin or it might be a mechanical element, and I need to convert the information that I kind of encoded in there by the sensing aspect to some other entity. For us, it's typically a microwave resonator, where you again need this conversion aspect. And then state transfer, this is kind of again in the direction of communication. What I also want to show to you is what I'm typically dealing is, so kind of my simple mind works in harmonic oscillators and two-level systems and their coupling. And I want to spend also a little bit on what interests me in this work. So for us, life as an experimentally looks a little bit like on this actual photograph of chip. So that's the neat thing. We have a silicon substrate, and we use fabrication technologies which are derived from standard silicon electronics by placing metallic films on there, doing lithography and defining all the quantum circuits on this chip in a planar fashion. This kind of cross-like structure, if you can see it here, that is a transmon qubit in this case. This transmon qubit is a multi-level system, but you can think about it in a simplistic fashion about a two-level system, and then you place and connect for example, a harmonic oscillator in this circuit fashion as a microwave system. Here, it's a distributed coplanar waveguide harmonic oscillator. And then they meet here, they interact, they couple, and this is actually kind of implementing already the Chaynes-Cummings Hamiltonian, and you harness this system for fabricating quantum states in the microwave resonator, for example. So you see it's relatively compact. So this chip is 6 millimeters by 10 millimeters roughly. It's engineerable. You can then think about connecting other systems which could be placed in here. You see then this is embedded in on a printed circuit board where you have all this microwave connection going in and out. It harnesses established fabrication techniques. The challenge is at the end the engineering part behind that, which can get rather complex. The low temperatures in the meanwhile, I would say, is not a big problem anymore. There are kind of commercial supplies where you would buy so-called dilution refrigerators, which place this system at millikelvin temperatures. And you need these millikelvin temperatures at the end of the day because these resonators, all these circuit elements operate in the gigahertz frequency range, and that gigahertz frequencies is roughly 200 millikelvin. So if you're at 10 millikelvin or so, you're in a thermal ground state or quantum ground state. What's getting more and more challenging in all these businesses is the complex electronics which is behind that. I'm talking here about room temperature electronics, and you can actually see the challenge already. So we have here a microwave line getting out. We have a control line controlling our qubit. We have a kind of an additional control line controlling the frequency of our qubit. And so if you think about scaling this for quantum information or quantum computing, you can actually estimate, this is 2 per qubit for kind of control, and several of these output lines for readout. This scales quite dramatically, and I think we will kind of see a huge development in this kind of conventional electronics sector in order to make these things. In particular, if you have things like that in mind, so the institute where I'm working, the WMI, there is also part of the so-called Quantum Valley. They are kind of working on scaling up quantum processing units and building quantum computers, and this is kind of the eye-catcher image where you see in kind of blue, these are all the qubits, so the kind of promises are big here, so 20, 60, 100 plus, and that means that we are talking about hundreds of microwave lines in the fridges, and the challenge comes from an engineering perspective. And to give you some idea that this is ongoing work, I'm pretty sure that you're aware of it. People started here this banner designs, and then it's now all in 3D integration, so kind of taking up on this kind of high density electronics integration from silicon and planting this on superconducting quantum circuits. This is kind of a long arching goal in this direction. So from a fundamental point, this is a super nice option for us as fundamental physicists, because we have access to highly coherent qubits, highly coherent quantum microwave resonators, so to say. So we are kind of taking the crumbs and can now build this relatively moderate effort quantum sensing, or kind of develop quantum sensing applications. And to remind you, so to talk a little bit more about these harmonic oscillator states, so you can either look at them in the Fock basis, which would be so the Wigner representation would look like this. You can look at this from a more classical pictures in a phase space diagram, where you see this red dot kind of only made one revelation, but we all know that for harmonic oscillator it kind of has some circular motion. But if you look from a quantum perspective, you will be limited in some certain uncertainty in the states, or eventually Heisenberg limited, where you're limited in the bits here of the state, kind of making your detection accuracy, or kind of uncertain detection uncertainty. And there, the quantum states that you could implement help us. So you have here this vacuum thing, and you have the vacuum state displaced, or a coherent state, which then oscillates here. And you can basically see here, if I plot then a squeezed state of this harmonic oscillator state, this is much narrower, for example, in the position direction, and you give up on the momentum direction, and there you can basically measure more precisely here in position. Or you can think about CAT states and say, okay, I want to use this interference fringes from these superposition of two of this displaced coherent states, and see that this is getting much sharper, much narrower, and then I kind of squeeze out some accuracy, and think about, first of all, what kind of benefit do I have from this, and second, as an experimentalist, also, can I implement this system? And for us, we do this in hybrid quantum systems. So we typically try to couple different modes of excitations. So take spins or magnets or spin ensembles and couple it to a microwave resonator, so depicted by this Wi-Fi symbol. Then we can connect a qubit for quantum state generation, or we can say, okay, I want to have a microwave resonator in this toolbox and connect it to a mechanical system. And then explore how we can get to these quantum states and how we can use or harness this for sensing. So this is the goal behind that, and it's not always straightforward to create these quantum states, I have to admit, and we are working hard to make this possible and kind of tweak out new tricks and think about in the direction how to do this. The physics behind this, the interaction Hamiltonian, basically what kind of interaction Hamiltonian, what kind of coupling Hamiltonian do we implement between certain entities, and then also what means that for the coupled dynamics. So that these are some of the big questions. And in this aspect, we were looking at various topics. So you basically have seen my toolbox. Now it's maybe getting a bit clearer. So you have these mechanical systems, so string resonators coupled to microwave resonators, or spin systems coupled to these microwave resonators. qubits coupled to these microwave resonators. You can also think about surface waves interacting with quantum states, or for kind of test reasons, we look also into coupled mechanical resonators. Okay, and for the sake of today, I want to kind of focus on spin photon hybrids in electromechanics, nanoelectromechanics. The first part is basically about this story, how far we got there, and the second part is about the spin photon hybrids. Any questions at this? Okay. So the sensing aspects or the sensing facet is, I think, quite obvious what you could do with a mechanical element. You can you have typically this mass on a spring with a rigid support, and this kind of does this oscillatory motion. You can measure the frequency omega m. There you can learn something about the spring constant and the mass, or the ratio of all of them. And in the spring constant encoded is typically mechanical properties of the solid which make up the spring. So you can learn about the string itself, or the mechanical object itself. You can learn about the mass, if you kind of think about mass loading, for example. So there's a mass measurement. From the displacement, you can also kind of look into forces and accelerations, how this kind of system interacts with an external stimulus in general. Unfortunately, we're talking here about, for our system, about picograms. And it's not so trivial to read out this picogram mass scale strings. And there's a trick, and this trick is kind of heavily used in optomechanics. This trick is that you couple this mass with this spring or this mechanical system to an electromagnetic circuit. This can be an optical circuit. This can be a microwave circuit. You take what you have or what you want to have, doesn't matter. And what you do is you translate the displacement of this mechanical system onto the resonance frequency of this oscillator, of this cavity, of this optical cavity. So it's think of it as a Fabry-Perot. The intermirror distance gives you the resonance frequencies. If I kind of slightly detune or kind of slightly displace here one of the mirrors, I can see this in this resonance in the cavity frequency. And you can do an amplitude motion detection, or you can do a phase motion detection, your choice. From the theory theory perspective, this is an optical resonator or an electromagnetic resonator, omega C, eta A. It's a mechanical resonator, coupled here, but this coupling Hamiltonian. And for me, this is typically more difficult to read. I'm basically thinking in this, I modify the resonance frequency of my cavity. There's a coupling constant and a displacement. And this G naught is nothing else as normalizing it to a 0-point fluctuation of this mechanical oscillator, so of the mechanics. So it's the capital G times the 0-point fluctuation. Okay. This is super generic, and in this nice overview articles, this was pointed out brilliantly. And you can basically take LIGO and do these physics. You can do Bose-Einstein condensates and do this physics. We do it with an electromagnetic circuit. And I will tell you a little bit why we think that this can have advantages. This Hamiltonian is inherently nonlinear. So you have this eta A, then this amplitude term E plus P dagger. And unfortunately, the G naughts that we are talking about are typically small. And the way around this is to go to a linearized description of this optomechanical Hamiltonian. That means that you shine in light onto the system. You can think about a Raman process and create sidebands to this light, and this can interact then with your microwave resonator. And this is then the relevant coupling strength is G naught times the square root of the number of photons in your microwave or in your photonic system. And then there are kind of the demarcations that this is either smaller than the line width of your optical system, it's larger than the line width of the optomechanical system. And if you operate in this regime, you are actually already pretty well off, because you can do a lot of nice things. You can do ground state cooling, you can quantum limited detection, you can do transparency effects. There's a lot of quantum optics analog that you can basically tick off and investigate in the context of mechanics. Unfortunately, you are satisfied and kind of annoyed by this at the same time, because you want to push harder and you want to go in this direction, eventually going to a strong coupling single photon regime where you have this bare G naught exceeding the line width of your cavity. And there you would be able to access phonon blockade, non-Gaussian states creation. So basically you take the full-blown beauty of this nonlinear Hamiltonian. There is a kind of intermittent regime which is called high quantum cooperativity, and this is a requirement which you need to fulfill to create. If you have a quantum state in your microwave resonator and you want to swap it into your mechanics, this is kind of the regime you need to be in it in order to do that sufficiently fast before your quantum state dies. There's another tick list from an experimental perspective. You want to be able to tune coupling at best. You want to kind of create stability in your system. All this in order to control everything correctly. Okay. We use microwave resonators, as I said. Mostly because we are from a low temperature physics institute. You can argue like this, or you can say, yeah, they are nicely engineerable. They are planar. You can design them, and you see a bit of examples for this design. This is a lumped element version where you have here an inductor. This is this meandering thing, and a capacitor. This is the digital object kind of shunting this inductor. So this is an LC resonator. You can go for a distributed network where you have a coplanar waveguide resonator. This is then some elements. You can typically describe this in an electrical engineering fashion or an equivalent circuit diagram. And the idea behind the superconductivity is just to kind of minimize the dissipation to get ultra high Q factors, because you always compare with this line width. And this R basically kills my line width. That's the main reason. We have mechanical elements. Actually, for sheer laziness, we want to be able to integrate this in the same material as the resonator itself. Therefore, we take typically aluminum and we suspend it. And you can think about it as a miniature micron length guitar string, where this length scale is roughly 20 micron. There's actually if you kind of plug in the values, all the strains that you have in your guitar is roughly comparable to this structure. It's just length scaling, megahertz frequencies. And the coupling, you need to now to implement this electromechanical or nano-electromechanical coupling. So you need a shift of your cavity frequency with a displacement. And I think it's super easy to understand this in this lumped element circuit diagram. So this LC resonator, what you can do is you can add a capacitance here. You have this capacitance kind of free to move. So full capacitance plates, this changes the capacitance slightly. And this translates into the total resonance frequency of this circuit. And that's it. And you can do some geometric estimates how far you can get with this. So these are kind of the most outstanding devices which are out there. You have these drum-shaped capacitors. So there's a top plate and a bottom plate. The bottom plate is on the substrate. And you can basically estimate how far you can get with this G0. It's related to the geometry of the device. So you have here micron diameter drums separated by 50 nanometers, which is kind of top-notch. The 0-point fluctuations of these drums is in the femtometer range, and that basically limits you. You can boost this by going closer, but it's super, super difficult. Okay. We are kind of trying to go a different route, and as this picture is quite intuitive, we are basically go for the complementary version, can we find an inductor which is kind of tunable by a displacement? And the answer is yes, and we are not the only ones to consider this. In roughly the 2000s, we and kind of many colleagues kind of picked up on this initially theoretical ideas to implement a suspended squid in a microwave resonator. And implement this optomechanical coupling experiment. And the story is about this device here, just because we did it in our lab, and I give you a kind of flavor of what it's about. So it's a microwave resonator, it's a coplanar microwave resonator, and it's shunted by a DC squid. People from the superconducting circuits community would say this is a flux tunable microwave resonator. This is well established. This is a Josephson paramagnetic amplifier. You name it. What's the special thing is here that we kind of think about the squid slightly differently. So what you have is that this squid is an inductor. It's a flux tunable inductor. That means that what the relative quantity is the flux penetrating through this loop. So this is kind of in this sketch, and we can tune this flux by applying a magnetic field, and we can change the flux through this loop by modifying the area. And that means that if we have a suspended squid, and if this kind of string is free to vibrate, we are changing this A, and that changes our inductance, and this changes our resonance frequency. And we do nothing less. The alternative is what you can do is you can change the B, so the magnetic field penetrating this flux loop. And this also changes this inductance. And the neat thing is then that you can tune the resonance frequency of your resonator by a magnetic field statically. So you see this characteristic lobe structure. And you have this kind of slightly wiggly fluctuations of the displacement, which are kind of a small modification of this here. And you then have the ability to tune the optomechanical coupling strain from an off state to an on state, for example. So you get tunability. And I want to kind of convince also you that you gain in coupling. If you kind of plug in this, you get to this G0 predicted coupling rate. It scales with the slope, which is kind of trivial to understand. It scales with the applied magnetic field. It scales with the length and the 0-point calculation of string. Okay. So how do we do this? So this is our resonator. It's shunted by a squid. This is an SEM image, a tilted SEM image of the squid. So we have here clamping points. We have here clamping points for our mechanics. So these are two suspended strings. Here are two Josephson junctions, and this is my squid area here. And we apply here an out-of-plane magnetic field. So for this angle, it's somewhere in this range. And for an out-of-plane magnetic field, so you can imagine there are kind of in-plane modes, mechanical in-plane modes, and out-of-plane modes. For both of these strings, they are slightly detuned because of geometry. You never get them exactly the same. We did an estimate, so the nanometer kind of imprecision in fabrication is totally doing it for you. And for an out-of-plane magnetic field, we are susceptible to this in-plane motion. What we then do is we need to check what's happening with our microwave resonator. And we do this with microwave spectroscopy. Basically, we look at transmission of this microwave signal. And if you want to know the details, we can talk afterwards. But I think it's that this is kind of too technical at this point. And if we probe microwave transmission, we initially probe our microwave resonator. So you see here gigahertz frequencies from 6.8 to 7.4 gigahertz. We basically measure a trace. We see here a kind of dip of our microwave resonator. There's our microwave resonator. We step our magnetic field, and then we see the slope structure that I showed. And you can analyze the slope structure and kind of convince yourself that you have this well under control. You can kind of get the slopes that I talked about here by numerical derivation. We're a bit concerned about line widths here in this kind of extremely tuned regimes, but they're still under control in the sense that the line width is manageable, or in the so-called resolved side width regime, meaning that the line width is smaller than the mechanical frequency. What you do next is you want to kind of check, do I have mechanics? And this is also, it's not simple to measure at the end, so the experiment is hard, but conceptually it's kind of simple to understand. So you have a microwave tone, and this microwave tone is basically scattering of phonons. So that means that you have a Raman type-like process where you scatter into a Stokes field or into an anti-Stokes field. And all what you do is you can freely set the frequency of this drive tone, and you can make it to scatter into the microwave cavity field and read out what's coming out of the cavity, for example. This is one way. You can also kind of tune this to the other side and then kind of scatter it to the anti-Stokes field, or you can even kind of set this here in the middle, and then you can kind of still monitor the residual fluctuations of this of the mechanics. And this is what you see here. This is the thermal mechanical fluctuations. So we are talking about 190 millikelvin here. That means roughly 500, 600 phonons in thermal equilibrium. And we are reading that out in sideband noise with roughly a photon or so, a microwave photon, which is decently extreme, I would say. And this is only possible because G0 is already kilohertz. And the question is, how do we get this further? So we checked if the scaling is correct. So on the back of the envelope calculation was basically this formula. We basically checked the dependence with this kind of prefactor, this slope. We checked the external magnetic field applied, the external, and we convinced ourselves that this scales as you would expect that it scales. And we would love to go to something like 70 millitesla, then we are in the hundreds of kilohertz range. Unfortunately, for this experiment, we used an out-of-plane field. And if you're in superconductivity, you know, there may be some flux lines, and you break some superconductivity, so it's not so smart to apply an out-of-plane field. So what is the next step? You just convince the friendly PhD student, go apply an in-plane field, and he says, because up to now we were in a fully shielded situation, kind of boxed in aluminium boxes, super nice protection from the outside magnetic fields. Now you get in a kind of conventional superconducting solenoid, and you apply kind of decent field. It turns out it works if you work hard enough. This is kind of minor point of active stabilization, and I'm just happy to show you that we can go up to 35 millitesla in plane field, which is roughly what we would expect for this layer stack of aluminum. We have 55 kilohertz. This is now on the red sideband because the tone is on the red frequency side of the cavity, and now we crank up here also the microwave power, so we can basically do an asymmetric scattering rate into this cavity, and here you basically suppress the scattering into the Stokes field because there's no free density of states, photonic free density of states. So you cool the system actively, and we get here this data set to 6 phonons. And we have new data sets where we get to 1 or 2 phonons cooling from a 600 phonon background. So we are approaching this vacuum state. We actually noticed from a mechanics perspective that these mechanics here are delicately depending on the applied magnetic fields, that the static fields that we apply, and we think that this has the potential to detect flux vortex lines which are captured in our strings. Okay, so I would like to conclude the first part of the talk. So I hope I could convince you that inductive electromechanics has some way forward, and we are trying to do in the upcoming EU project quantum state preparation and
Can I ask a question?
Yeah.
Here, so I didn't understand what you gain with the in-plane magnetic field. So what is the difference?
the difference is so if you apply an out-of-plane magnetic field into a superconductor thin film, then so there's a geometry factor basically in there. So you basically the Meissner phase would kind of tell you, yeah, I want to go around the superconductor, and this costs you a lot of energy because of large surface areas. And if you basically apply an in-plane magnetic field, then this displacement or this field distortion is minimalistic, and that is one of the reasons why you can get to larger in-plane fields than out of plane. You would call it demagnetization in magnetic. Yeah.
The increase of coupling when you say the 7-inch Tesla. So I didn't get exactly how it scales. I mean, I thought this goes with the kind of sensitivity with, I mean, it's periodic flux, right?
Yeah, you have basically two things. So this G naught scales with the slope here.
Okay.
So you want to operate at one of these extreme points,
But
but it also scales with the external field because you basically have the factor which kind of interests you is the flux through the loop. The total flux, which you modify when you have a field. And this total flux is that you modify is the amplitude times the length of the string times the magnetic field, which is static. So this is the reason why you have an external flux and why more flux helps.
So you want to work on that point, but maximizing experiment.
Yeah, which is non-trivial experimentally. And you can think about niobium nitride instead of aluminum and all this. We are thinking about this. We are presently, so we presently think that we are reduce the microwave kappa by improving the interfaces at the silicon aluminum. So there's a lot known in the community about how to produce ultra high quality factor microwave resonators. And we're following up this route because our estimate is that we should get to quality factors of about 400,000 in this magnetic fields. And that should be totally sufficient. But we need to do this a bit in there. So. Okay. Moving from mechanics to the spin photon hybrids it's basically in the same footprint that we use a microwave resonator. Fabrication, as I will tell you, is getting much more straightforward. It's kind of super low tech. And whenever I say spin, or in this case, what I will talk about today is a spin ensemble in a microwave cavity, as kind of shown here in this artistic depiction. You can replace a paramagnetic spin ensemble with a exchange coupled ordered magnet as well. There's no much difference. And in order to bring home this point, I would like to kind of take a step back and remind you about the classical equation of motions of the spins or magnetization in a magnetic field. So this is a classical depiction where you have a magnetic field, a magnetization, and if you have some tilt angle between them, there's a Larmor precession going on. You kind of measure here the Larmor precession frequency, and if you would do magnetic field sensing, your job is to measure this Larmor precession frequency as precise as you can. That's the idea. Okay, in order to create this tilt, you typically use a drive. This is for us a microwave excitation. There are other other works where you can excite this differently, but I won't touch upon this. And this is old stuff, or that old stuff, as I would say, because this has all been kind of established in the mid-40s. So in a classical picture as well as in a quantum picture. So what is kind of the alternative viewpoint for this picture is you have a magnetization in a magnetic field. So you can take the standpoint that I have n spins and I couple them to a total magnetic moment and I apply a magnetic field. That means that I have I lift the degeneracy of the magnetic quantum number in energy, and I label it from n minus n over 2 to n plus over 2. It's a simplified version, I admit this, but it kind of brings the point home. You count excitations, 0 excitation, 1 excitation, 2 excitations. What I want to say is this is an harmonic oscillator for low excitation numbers. And Akash would come to me and say, yeah, but you could do Holstein Primakov and all this, and be way more accurate. And they say, yes, you can. This is my naive picture. What you do then is, or what you need to do is you place your magnetic system in your microwave resonator, and you want to maximize this coupling G effective. And my theory intuition there is that it's a dipole magnetic coupling, and in rotating wave approximation, you just kind of you swap excitations between the spin system and this microwave system, and the total Hamiltonian includes the microwave cavity, the spin system as a spin harmonic oscillator. They have a couple two harmonic oscillators by a so-called beam splitter Hamiltonian. That means that I can swap excitations. And this collective or effective coupling strength, G effective, scales with a G naught. In this case, this is a single spin coupling, typically 50 hertz, so times the square root of n. So we are talking about large numbers of n, typically. N is the number of spins here. Okay. And so I typically like to write this slightly differently. And the reason is the following. So I pack spins in this gray shaded area. That means this is my mode volume of my microwave resonator. And only spins in this mode volume can contribute. So I can fairly say that if I know about this mode volume and the spin distribution in here, I can replace this n by a spin density and a filling factor. And this helps me for engineering purposes, because I know I want to have as much filling as possible, and I actually would like to have as a high density as possible. And for paramagnetic systems, there are limits, because at some point the paramagnet decides to talk, that the spins talk to each other, which I do not want. For an exchange coupled magnet or an ordered magnet, this rho is kind of immense. It's kind of 1 spin per atom, roughly speaking. So you can boost here by going to a fully ordered magnetic system quite dramatically. What I told you with the Hamiltonian can be subsumized in this kind of mechanical analog. You have two pendula, they're coupled with a spring, and what you do is you exchange excitation from green to blue and vice versa. And we all know how this works. We want to have here a high quality resonator, a kind of a long-lived pendulum, and here a long-lived pendulum, otherwise you're damned out. And that's what's meant under the strong coupling regime, that this collective coupling strength, this coupling here exceeds the loss rates. If you do that, and if you are able to kind of tune the resonance frequency of one of these pendula, you would see a normal mode splitting or an anti-crossing, or however you want to call it. And this is what you want to see. Oh, easy. What would you choose as an experimentalist as a system? It's a spin system. In this case, we chose phosphorus, donors, and silicon, because you can get it in an isotopically engineered fashion. That means that the coherence times are promised to be in the seconds, nuclear spin lifetimes in the hours. So that's lunchtime experiments, coffee drinking, potential yeast coffee drinking. What it actually turns out, I told you the story about the densities, the spin density. You want to crank up, these numbers go slightly down, but you will see we are living with milliseconds, so not too bad. And for this particular system, you have a nuclear spin and an electronic spin, and the electronic spin does the same interaction, the nuclear spin as well, but what you are dominated with at these frequencies and fields is the hyperfine interaction, and that gives you two microwave transitions to yeast. We always do the same things. We do microwave spectroscopy now in a time domain fashion, but this here is kind of, it doesn't change. And the low-tech solution is that you have your microwave resonator and you glue a crystal on top. That's it, literally. And then a little bit of glue over it, and that's doing it. We did, actually, we invested into engineering these things, and the reason is to get the mode filling, the mode volume filling correctly. So these resonators are designed to have a nice field distribution, a V1 field distribution, which is matching our isotopically engineered silicon crystals. So our crystal is roughly 20 micron thick, and it kind of covers most of this resonator to get these high collective coupling rates. What you see is microwave spectroscopy wise, so you do ramp or you measure the microwave transmission as function of the microwave as function of the magnetic field. You see these anti-crossings that I was talking about, and another anti-crossings. So these are these hyperfine split phosphorus donor signatures. You see that there's a slight modification. And the slight modification is basically that you are so sensitive that you see effects as a silicon dioxide interface. You can see clusters of donors because you have now 10 to the 17 donors, and there's a statistic in the distribution or in the separation of them, and some are sufficiently close that they interact with each other with a direct interaction, and they show up here. And the neat thing is that with these P2 clusters which appear, and this is strongly coupled in isolated donors, you have a system where you can compare the strong fields, the strong coupling case with the weak coupling case. And if you are there, then for the people who are doing electron spin resonance, the next step is pulsed sequences. The pulse sequence that you would kind of try is the Huebl sequence, because it has its key applications in what's the coherence time of the system. It's kind of a basis for control of the spin configuration, things like this. And the idea behind the Huebl sequence is that you flip your spins into the equatorial plane. They disperse, so because of is the diffusive process, you revert this process by a 180-degree pulse. They refocus for this echo, and then they disperse again. So they diffuse again, and you never see them again. And you repeat this experiment with a time which is compatible to T1 or exceeding T1, the spin lifetime. Okay. We thought about this, we did this. If you do this, you get to your 6 milliseconds T2 times. These are all single shot experiments because it turns out that our T1 time is in the ballpark of 10 seconds to 30 seconds. So every shot is 3 minutes, 5 minutes. And then we just kind of have enough signal to noise that we get away with single shot experiments. We actually did this acquisition, but we have our home-built setup. So we have a digitizer which is running also kind of in this direction longer. And then we were kind of scratching our heads because we expected, as I said, this first echo, but all the subsequent echoes, they shouldn't be there. And the question is why? What's apparent in this diagram is, so this is the weak coupling P2 peak. There we have our echo, that's no problem, but it's gone. you can actually convince yourself that you should have enough resolution that you see subsequent echoes, but you don't. And we then sorted out this already complex but still graspable picture. So we start with flipping it to the equatorial plane. The spins disperse here on this equator. And you can identify spins at point 3, so short before tau is there, that made it multiple times of 360s and multiple times of 360 plus another pi. So that discerns basically the red spin from the blue spin. These are always many, but you can subsumize it in that. And then you do an imperfect pi pulse. And what happens then is that the red spin is encoded to the northern hemisphere and the blue spin is encoded to the southern hemisphere. And they refocus as usual here, but due to the enhanced coupling rate, they decay. They are now, the red spin is here in the equatorial plane, the blue spin is kind of pointing a little bit more downward. But you encoded here a number of revolutions. From here to here, you know that basically this subset will kind of reappear here. This subset will reappear on the other side. So between here and the next echo, this is between 6 and 7, you know that the blue spin will kind of have an extra pi, the red spin not. They all refocus there, and there's a residual in-plane magnetic moment which kind of produces this add-on echo. And this is the story where this comes from. You can use Maxwell equations to calculate this. I refer here to my theory partners because I can't, admittedly. The neat thing is that you have then information what happens with the spin states and how this dynamics come about, and the question is if we can use it and if there's kind of some features. And this would be the second part here. You have, we talk about strong coupling and these self-stimulated echoes, and the upcoming questions is basically how to twist or kind of harness our superconducting quantum systems to, for example, create spin squeeze states that would be interesting, or more complex quantum states in these spin systems. So with this, I would like to leave you with this overview slide and open questions.
So any questions? I have any questions, but I will start. When you talk about the number, when you reduce the occupancy of your mechanical core using this anti-stores, I'm curious whether you compare that to having a low temperature, right? You call it cooling. But do you know, I mean, is there a role of chemical potential there? Because I think what you can look at is M, but can we rule out that the chemical potential is not becoming non-zero?
So what you do with this, so it's typically called cooling, but it's a specific mode cooling. So it's not that the friendly temperature of your solid changes, right. You're only cooling this specific mode. But if you stay in the frame that you're only talking about the thermal occupancy or the state occupancy of this mode, you should be able to apply also these features.
Even for one mode, I could imagine that the occupation can be influenced by the chemical potential or the temperature. So if you assume chemical potential, but I guess that's what I'm saying, you assume chemical potential to be 0 and then you find the temperature that corresponds to the occupancy. Are there any questions online?
The last part, so I understand you use kind of ensemble of spins, right? And the magnetization as quantum states. So connecting to like your motivation of quantum technologies and things like this. It would just kind of be an interesting platform, let's say, for quantum qubits or
so these states, these spin states, they're long-lived and therefore they basically have two functions, or we are presently considering two functions. One is a memory function. So there is so you need, or you would like to have quantum memories for quantum repeaters and these applications in order to time the delays between quantum signals. And for this, we are working on this and presently try to work in the direction that we store quantum states in the spin ensembles. There, the idea is that we prepare a microwave quantum state beforehand and swap it into the spin ensemble and try to read it back out again. And the initial line of thought is that groups in the WMI know how to prepare a squeezed quantum microwave state, and we just use this or replace the initial pulse with a squeezed microwave pulse and check out what's happening there. And if we get this out again, if you think this through, this demands certain parameters in the readout rate. So you need to implement a very efficient readout from the spin excitation to swap it back into a microwave excitation and get it out again. And this is presently the challenge of what we are working on.
So
And for sensing, it's basically we can use it for both things. For sensing, you would say, okay, I prepare a squeeze set at one of the poles, and then I swap it into the equatorial plane. And the simple picture is basically that you don't have a vacuum state, which is then a blob on the equator, which is oscillating with the Lama precession frequency, but you have basically a better phase distribution, and you squeeze the information on the equator, which you outcouple to the microwave state. And that should give you a higher sensitivity in terms of magnetic field sensing, if you can prepare this state.
May I ask a question?
I didn't get the role of density when you saw the strong coupling constant.
Yeah.
Coupling constant. You mentioned that eta was the filling factor.
Yeah.
And then you had the density, and then you mentioned that reduced the lifetime. I was wondering if those spin-spin interactions would be an opportunity to induce some anharmonicities, as you mentioned in the Prima code. I mean, when you talk about the CAS and the is there anything good that can come from the spin-spin interactions that system?
Yes, of course. So we haven't thought about this in detail because the way our experiment presently works is that if they interact, they are kind of sufficiently separated in magnetic field. So you can really identify, okay, this part shouldn't kind of, so they're basically, the transitions that you see there, they're kind of spatially separated in magnetic field, and therefore you have the advantage that you can say, okay, I'm only looking at this transition and I'm reducing my mindset to an effective two-level system. And they are doing roughly all the same, and the distribution is with interaction with other spins or with nuclear spins is kind of drastically reduced because you engineered your silicon to be nuclear spin free. I agree that you could do something there, and we are presently discussing how to combine or to so in electron spin resonance, there's kind of a sub-interest in questions of how you can manipulate nuclear spin and electronic spin. And we are presently trying to reconsider that because there are many tricks of how to polarize your nuclear spin system. So the coupling to the nuclear spin is kind of next on the agenda, but we try to keep it simple at the moment.
So basically, you have capabilities that go beyond the imagination.
It's painful at the same time. That's what, that's what I can tell you.
On the screen, look.
Yeah. On the screen, it looks nice. That's the wonder of PowerPoint.
Yeah, in the first part of the talk, what do you mean by 0-point fluctuation and why does it affect the coupling?
To understand your question better.
Yeah.
Yeah, I think this coupling, when you have optical cavity,
Yeah.
you assume one mirror to be fluctuating.
Yeah.
So she's asking to specifically state what 0-point fluctuations mean and also why does that enter the coupling strength? So I think the very first.
Oh, okay. Yeah.
The 0-point fluctuation is really that if you have something which is movable, then Heisenberg uncertainties will tell you that it cannot be at rest because delta x times delta t is finite. And if something is at absolute rest, it has 0 p and a finite x. That's not allowed. So everything has 0-point fluctuations. So that's 0-point fluctuations, but why does it enter the coupling?
So I wanted to get this slide. So we basically asking this question here. So this picture can be understood fully classically. You just do a parametric readout of a position with a laser, for example. So you and the optical alternator makes it better, so to say. And there it's kind of pretty clear what you expect as a frequency shift for a certain displacement. Okay, and then you know that this is an harmonic oscillator. If you write down the quantum mechanics version of a harmonic oscillator, you would typically either go for real space coordinates, but my friendly colleague from theory would tell me, yeah, but you normalize into we normalize coordinates x and t, and this normalization for the x direction, this is this 0-point fluctuation. So you would kind of say this is just a normalization factor, but the meaning at the end of the day is that, and you tell me if I'm wrong in my understanding, that you have basically, if you have 0 excitations in the system, this is roughly what you would expect as a displacement of this object. The center of mass displacement of this. And what you then say is, okay, the coupling strength, how to get to the coupling strength in a quantum picture is that I want to write everything in second quantization.
Yeah.
But I know that here for the second quantization, everything is normalized out in this kind of pre-normalized coordinates. And all what I do is, if I write the norm in this fashion, is I have this 0-point fluctuations. The 0-point fluctuations times the amplitude get me to a real amplitude.
Thank you.
So it's kind of a normalization factor in some sense, in order to convert in second quantization between these normalized coordinates to real space coordinates. Because this, at the end of the day, is a real frequency. So here you would have some meters. Here it's frequency per meter, and in order to get this fixed, you would write it that way.
One question.
Yeah, I have one question here from Walter Arnold. He asks, what determines the decay time of the spin echoes?
So for us, so the question is, so what determines the decay time for the spin echoes? So what you would like to consider is the following, that you have, I'm now dancing into the camera, so you're getting into the equatorial plane. It just uses.
May I?
In principle, if everything runs perfect, every diffusion, you could refocus. But think of it as running on a 400-meter track. So it's basically the same game. You have a starter kind of shooting the gun. The people start running. And then
I understand that.
Again, then the idea is that you turn around in a zero time frame, and then you basically run back with the same speed, and everything kind of refocuses.
Yeah. I understand that. I worked myself on spin echoes.
Person A struggles and
That's
gets out of phase with him or herself, and then this person has what people would say it's a decoherence effect, and this is the reason where you can basically count people lost in or spins lost in this rephasing.
I'm sorry, this is not what I asked.
Therefore, it's called a coherence. And then there's a kind of underlying question is, where comes this process, where does this process come from? Is this magnetic field fluctuations, which are different in the first and the second half of this refocusing part, because the assumption is that the field in the first part is the same as in the second part of this kind of mirrored around this 180 degrees pulse. And if you have magnetic field noise, that could contribute. If you have other noise of any sort and kind, this all could contribute and change or cause this decay. You can actually learn a lot about which mechanism is at play, and there's kind of spin-spin interaction is coming at play there. And we took care to kind of rule out kind of some of these effects you would be able to see in this dephasing also interaction with nuclear spin. So then this naively expected exponential decay would look differently, and then you would say, yeah, we have the spin diffusion loss. So
I'm
there's
actually
a lot of knowledge in the EPR electron spin resonance community about what happens there, or what could happen there, and to be frank with you, so our coherence times are significantly better than we would expect for this spin density. And we don't fully understand why they're kind of significantly better.
Yeah.
And significantly means an order of magnitude. So
I'm
for the spin density that we have, our coherence times is a factor of 10 to good. We are not complaining, but we would like to understand this physicists.
I'm actually online. I wanted to know to which elementary excitation.
Thank you very much, Hans, once again. Coming back to the common points of the